Hi Algebra 2 students, this is Mr. Chun, and this is lesson 6 in our unit on rational, exponential, and logarithmic functions. Today we're going to be talking about how to evaluate logarithmic expressions, and how to solve logarithmic equations. So remember that an expression is something that doesn't have an equal sign. An equation always has an equal sign in it. Okay, so let's start with the definition of a logarithm. What is a logarithm? Well, here's the mathematical form. Let's read it first. It says, suppose b is greater than 0, so b has to be a positive number, and b cannot be 1. Okay, so it's a positive number that's not 1, and for all x that's positive, there's a number y such that this statement's true. All right, the logarithm base b of x equals y if and only if b to the power of y equals x. Okay, so what it's saying here is this is true only if this is true, and this is true only if this is true. You can see here that these three numbers are going to be the same. Okay, they're the same variables, they're the same in this situation, so this statement is equivalent to this statement. All right. And really, this statement is just rewritten as an exponential form, as an exponential expression here, equation here. And this is rewritten in logarithmic form. So they're really just saying the same thing. We're just shifting the numbers around and removing the log over here. Okay, so let's look at some examples of this. Before we do that, this is read as y equals the log base b of x. Okay, so that's how you'd read it. Make sure you can read it properly. That's part of good communication. And the key here that I want you to know is that logarithms are inverses of exponential equations, okay, or exponential functions. Okay. Here's a picture to kind of help you see this. This here is an exponential equation, y equals 2 to the power of x. And that's this graph right here. Notice that this, I believe, this is our, this here is our x-axis. This is our x-axis. This is our y-axis. You can see that we talked about this graph quite a bit. Here's my line y equals x, and if you flip the x and y values, if we switch the x and y values, okay, so here's our x values, here are y values, if we flip them, that's finding the inverse, right? And you can see here that we end up with this graph. And this graph actually turns out to be the log function, okay? So this actually turns out to be the log function of, it's the log base 2 of y equals x, all right? So let's try to convert something that's in logarithmic form, an expression that's in logarithmic form, and change it to exponential form. Okay, remember from our previous slide that we said this can be rewritten in exponential form. So let's do that. Okay, we said the log base b of x was y if and only if, and I'm going to use an abbreviation here, if and only if b to the y is equal to x. Okay, so we can rewrite this. Let me show you a little trick. This b here, if I move it up like that, move it to the other side and remove my log, and then I end up with b. Pretend that the b pushes the y up and the y becomes small, and then I get rid of my log and the x stays over here. Okay, this is what I get. So that's kind of a little trick that you can use to help you rewrite when you're converting from log to exponential form and from exponential to logarithmic form. So let's go back to this example. Let me just write it over here. I have the log base 3 of 81 is equal to 4. Okay, so what I'm going to do is I'm going to move my 3, log base 3 of 81 equals to 4. I'm going to take this 3, I'm going to move it, it's going to bump up my 4, like that. My 4 becomes small, and then I end up with that. I get rid of my log, and that is my the same as this statement written in exponential form. Same thing with the log base 2 of 1/8 equals -3. This 2, I'm going to move over here. That becomes really small, so it becomes a small 3, -3. We end up with a big 2 on the bottom, and that is an equivalent form of this statement written as an exponential form. Okay, so these are the nice, neat solutions that you can see as well. Okay, let's try a few more. This time we're going to go from exponential form to logarithmic form. We're just going to go backwards. This time we're going to drop the 3 down. The 3 becomes big. The 2 goes down over here. It gets small. Maybe we end up with log base 2 of 8. So all we're practicing here is rewriting them, switching from exponential form into logarithmic form, from logarithmic form and switching into exponential form. So that's the same statement in logarithmic form. Let's try it again. This 4 comes down here. It becomes a little 4. That 2 drops down. It becomes a big 2. Okay, so we end up with 2 equals, and then of course we have to add the log here. Little 4, base 4 of 16. Okay, and same here. Bring the 2 down. We end up with 1/8 inside my log. Okay, so we end up with a log base 2 of 1/8, and then that -3 drops down and it becomes big. Okay. One more thing I just wanted to mention before I move on is that this number is called the argument. Okay, that's called the argument. That's the argument. That's the argument. Okay, so you can see that the argument is the number that is that the log is being applied to. Okay, when I say log base b of x, that is my argument. Okay, and that's of course called my base. Okay, so that's just some vocabulary here. That's the argument and that's the base. Okay, so just keep that in mind as we move on. I'm going to be referring to the argument, so just so you know what that is. So let's take a moment. You pause this video, try numbers 1, 3, 1, and 2. Try them, and then I'll show you the answers. Alright, so here are the answers. Okay, you can see here that 7 squared is 49. That, if we rewrite it, we drop the 7 down, put it near to the 49, okay, and we get that. And the other side, the 2 comes down, we get a 2. Okay, so that's correct. Same thing with this one. We drop the 10, move it to the other side. The argument is now 1 over 100, and that is equal to -2. Exponential form, we move this up, okay, and same thing here. This argument gets isolated over here. The 5 moves over to the other side, bumps up the -3, and we end up with that. All right, you'll get some problems that say evaluate this. Okay, evaluate log base 3 of 27. Well, what evaluate really means is it's saying find an equivalent number. Okay, so simplify this. Let's make it a nicer number. Let's evaluate it. Let's find an actual, real, simple answer to this. And the way you're going to do this is you're going to set this equal to x. Okay, because that's going to be my simple answer. Okay, so we don't know what it is yet. We're going to set it equal to that. And now you just need to rewrite it in exponential form. So we're going to take this 3 again, and we end up with 3 to the x, because the x gets bumped up. We end up with 27. And now this is just like what we did in 9.1. Okay, we're going to have to rewrite this in terms of base 3, because we want to isolate what that x is, right? So this becomes 3, and you're going to need to know your multiplication tables. 27 is 3 cubed, and that ends up being 3 to the x. So we can drop the exponents down, and we can say that this is equal to that. So x is equal to 3. All right. Okay, so this is a nicer solution, neater solution. Okay, these are some characteristics of the logarithmic function that I would like you to know. The function's continuous, and it's 1-to-1, which means it passes the horizontal line test. Remember that the horizontal line test indicates whether a function's inverse will also be a function or not. The domain is always going to be the set of positive real numbers. Okay, so let me show you a quick graph. We talked about this graph earlier. Okay, this is my line y equals x. This is this graph right here in red. That's going to be the graph of a log function. Okay, and that point is always going to be 1, 0. Not always, but it depends on what my a value is. But if this was the case, okay, then this graph would represent that log function. Okay, so you can see here that the domain is going to be the set of all positive real numbers. Okay, this graph does not exist way over on this side. Okay, the graph doesn't exist. This just keeps going down, down, down. This keeps going up, up, up like that. Okay, so you can see that there's going to be a vertical asymptote, and that's what number 3 is. The y-axis is an asymptote of the graph. The range is all real numbers because I can have y values that keep going up over here and y values that keep going down. The graph contains the point 1, 0. Okay, and that's the same as saying the x-intercept, the point where the graph crosses the x-axis, is 1. All right. Take a moment to think about this. Why is the log base 2 of -8 undefined? Well, I just said it. The domain must be set to include only positive real numbers. Okay? So that's why this is undefined. This expression does not exist, and you can try this on your calculator. You'll get outside of domain or undefined or something like that. Okay, so let's look at logarithmic equations. We've talked about how to solve or how to evaluate logarithmic expressions. Now we're going to talk about equations where we now have an equal sign and we're looking for the value of an x. Okay, when we evaluated the logarithmic expression, really we were creating an equation, and so this shouldn't be much different. But before I move on, I really want you to know this. The log base b of 1 is equal to 1, okay? And the log base b of 1 is equal to 0. Now these, you must know, you must be very familiar with these because they'll come in pretty handy. So I would put this in your notes, put a big star or circle around it or a box around it, make sure you know it, okay? And let's just think about why this would work. Okay, if I have the log base b of b equals to, and I say, let's evaluate this, where b could be any number. Obviously, b would have to be a positive real number, but let's say it's equal to x and I want to evaluate it. Well, if I rewrite this, I'm going to get b to the x equals b, won't I? That log is going to disappear. And what is now, because my bases are the same, I can set my exponents equal to each other. Well, this exponent is actually just 1 because anything to the power of 1 is itself, and so we can say x equals 1. Okay, so that's why this number over here is 1. Same thing with this example. If I move my base over to the other side, let's set that equal to x because that's what I want to find out. Well, if I move it to the other side, move my base over here, I get b to the x equals 1. Okay? Well, oops, sorry, not 0, that should say 1. Well, any number to the power of what is always 1? Well, anything to the power of 0 is 1. Okay? So x has to be 0. Anything to the power of 0 is 1. Okay? So that's why this statement and this statement are true. These are special log values, and you do need to know them. Okay. All right. So let's take a look at another example. Solve for x. How can we find this x value here? Notice that this is the argument. X is now inside my log function. So we must make sure that this number, whatever this value turns out to be, that it's positive. Okay? So if this number turns out to be negative, then we're going to end up with an undefined logarithmic expression, and there will be no solution to this statement. So let's rewrite this in exponential form. We're going to rewrite that 6 goes up, so it becomes x equals 6 squared, and x equals 36. This is positive, so this is my solution. It does work. So always check after you get your answer. Let's try this other one. Log base 5 of 1 over 25. Well, that 5 will move and bump up the y. So 5 to the y equals 1 over 25. Well, 1 over 25 is 1 over 5 squared, and 1 over 5 squared can be rewritten as 5 to the negative 2. Okay? So we can say y is equal to negative 2. Now, could this be a real answer? Is this a possible answer? Yes, because the range is all real numbers. So this does work, and this also works. Okay, and these are my neat examples. Okay, if you recall from the previous section also, we talked about if b of x equals b of y. Okay, and I'm just using x and y. I could have used different variables here, but let's just go with this. If I have two numbers and they are in the same base and they have different variables in their exponents, then we said that x equals to y, right? Well, it's the same thing here with logs. Okay, same thing here with logs. If the log base b of x is equal to the log base b of y, then x equals y. Okay, so if the outside part is the same, then I can set the arguments equal to each other. Okay, then simply set the arguments equal if the bases match on both sides of the equal sign. Let's apply some. Okay, you can see right away here that the bases or the logs are the same. They have the same base. They're both log base 3. That's really important. If one is log base 4 and one is log base 5, we wouldn't be able to do this right away. But because they're in the same base, we can. So we're going to set the arguments equal to each other. 4x plus 10 equals x plus 1. All right, 4x minus x is equal to 1 minus 10. And so we end up with 3x equals minus 9. X turns out to be negative 3. Am I done? No, because I need to check to see if this is a real answer. Will this make my statement true? So this is what I get mathematically. Let's check it back by plugging it back in. Well, we end up with log base 3 of negative 12 plus 10 equals the log base 3 of negative 3 plus 1. Okay, both of these turn out to be negative 2. So this is no solution because we can't have a negative argument inside the logs. And so we would say no solution. Okay? And this is the same thing, but just make sure that you check it. We've checked it, it doesn't work, so there's no solution. So it says solve. Well, we're going to say there's no solution. There's no value of x that makes this sentence true. Let's try another example. We can see here again that the bases are conveniently the same, so all we have to do is set the arguments equal to each other. X squared minus 14 equals 5x. And this is actually going to be the same type of problem that we had in chapter 5 when we were doing quadratics. So we're going to do x squared minus 5x minus 14 equals 0. We can factor this, and we end up with x 14, that's 7 and 2, 5, so that's minus plus, right? So my two answers will be x equals minus 2 or x equals 7. Okay, now we said we have to always check both of our answers, check to see which one of these will work. Well, x minus 2, if I plug it in, this ends up being minus 10. So that can't work because my argument cannot be negative. So this is the only one that will work. Okay, 7 squared minus 14, that's positive. 5 times 7, that's positive. So this is my answer. My solution set would actually be 7. Okay? All right. And that is it for this lesson. This is your assignment. So please take a look at this and let me know if you have any problems.